So in this lecture, we're going to actually walk through an example of the ANOVA. Again, this is a between subjects independent ANOVA. So we're looking at the fact that we have independence between the groups and we have three groups. So again, we want to determine our hypothesis. That's always going to be the first step of computing anything. What is the hypothesis we're testing? We're then going to set our criteria for significance, determine the alpha. This is usually going to be a p of 0.05, though there are some rare cases where it might be different. We're going to calculate the degrees of freedom. We're going to find the critical region in the F distribution table that we need to exceed for us to claim that statistical significance. We're then going to compute the sum of squares within and between, compute the mean of squares and find the F ratio, and then compare the F ratio to that F value to state the conclusion. So we're going to walk through this entire process, including how to hand calculate an ANOVA and what steps are necessary once we've actually done that omnibus hand calculation. ANOVAs do get complex, but they can still be hand calculated, and we're going to walk through a simple way to do that. So usually the best way to actually do any hand calculations is to actually create a table. In this table, we've got three different groups. We've got a criminal group, a non-criminal group, and an unknown group. So we basically have a group of 5 individuals who we know have a criminal history. We have 5 individuals that we know do not have a criminal history, and we have 5 individuals that are unknown. So the degrees of freedom within is the number of people in each condition minus 1. Now notice that with the hand calculations, there is an assumption that we have an equal number of people in each group, even though they're different people. This is not an actual requirement of ANOVA, but it becomes a more complex set of math to do if the ends are different. So for the purposes of exercise in this class, we're always going to assume that we're working with a hand calculation sample of equal size in each group. So we have 5 people in these 3 groups. What we need to now do is calculate the mean of each group. So for the criminal group, we actually have a score of 10, 7, 5, 10, and 8. It's a total of 40. 40 divided by 5 in the criminal group means a mean of 8. We now create a list of the deviations from that mean. So 10 minus 8 is 2, 7 minus 8 is negative 1, 5 minus 8 is negative 3, 10 minus 8 is 2, and 8 minus 8 is 0. Again, we're taking the individual person's scores, and then we're subtracting the mean. That becomes the deviation for the mean. And then we're going to square this. Once again, F's are always going to be a positive number, so we want to get rid of those negative signs, and the easiest way to do this is square this. So 2 times 2 is 4, negative 1 times negative 1 is 1, negative 3 times negative 3 is 9, 2 times 2 is 4, and 0 times 0 is 0, and we sum this up. And we get 18. Now, to get the sums of squares, we also need to take into account the degrees of freedom. Remember, it was n minus 1 for each group for 4. So that 18 needs to be divided by 4, 4.5. We now have the sums of squares for our criminal group. We're just going to do the same thing for our non-criminal group. Again, we're going to add it up. We have a total of 20 divided by 5. That means our mean is 4. And again, we're going to take each person's score minus the mean and then square it. That gives us a value of 20. That 20 then is divided again by the degrees of freedom within. N minus 1 equals 4, which is a 5. And we're going to do the same with our unknown group. So again, we calculate the total of means. In this case, it's 25 divided by 5, which equals 5. We're going to subtract 5 from each score. Excuse me. We're going to square it. And then we're going to take that final value, once we've summed up the square deviations from the mean, 26, divided by the degrees of freedom within, n minus 1, which is 4. That's 6.5. So we now have a total variance measure for our criminal group, 4.5, a total variance number for our non-criminal group, 5, and a total variance number for our unknown group, 6.5. So again, our MS squares within is we're simply adding those numbers together divided by the number of groups. So 4.5 plus 5 plus 6.6 is 16, rounded. And then we're going to divide that by 3. It becomes 5.33. We now have the bottom of our equation. That is the value that represents the total variance within all of these groups. Now we need to get the top of the equation, the difference between the groups. So in this case, we're actually looking at, again, we're looking at those means. So we have the means already. We have the mean of the criminal group of 8, non-criminal group of 4, and unknown group of 5. What we now need to do is calculate the grand mean for everyone. In other words, across these three groups. So we add 4 plus 8 plus 5, it becomes 17. And we divide by 3. That means that the grand mean for all three groups is 5.67. We're now going to subtract 5.67 from 4, from 8, and from 5. And then we're going to square that number, again, to get rid of the negative values. So 4 minus 5.67 is negative 1.67. 8 minus 5.67 is 2.33. And 5 minus 5.67 is negative 0.67. We're now going to square those. So negative 1.67 times itself is 2.79. 2.33 times itself is 5.43. And negative 0.67 times itself is 0.45. And we're going to add those up. We're going to sum the squared deviations from the grand mean. That becomes 8.67. We now need to actually divide it by the degrees of freedom between. This is the number of total groups minus 1, so 2. So 8.67 divided by 2 is 4.34. So our sums of squares between is basically our sums of squares that we just calculated times the actual number of people that are in each group. Again, we're assuming an equal number in each group. In this case, it's 5. So the total is that 4.34 we just calculated times 5, which is 21.7. We now have the top of our equation. So at this point, we now have the top and bottom of our equation. Our MS between is 21.7. Our MS within is 5.33. So 21.7 divided by 5.33 equals 4.07. That is our F. We have a calculated F for this particular sample of data. We do need to go our degrees of freedom. Again, our degrees of freedom between is simply the number of groups minus 1. So in this case, 3 groups. Minus 1 is 2. And the second one is our degrees of freedom for each individual within group minus 1. So 5 minus 1 plus 5 minus 1 plus 5 minus 1, which is equals 12. So the degrees of freedom within is the number of people in each group minus 1 summed, or another way to think of it is just add up the total minus the number of groups. There's 3 groups, so 15 minus 3. This both gives you the same value of 12. So we report this as F, parentheses, 2, our first degrees of freedom between, and then comma 12, our second degrees of freedom within, and then the value, 4.07. We now need to find out if that final part of the equation, p less than 0.05, is actually correct. And how we do this is we actually, again, go to the charts. At this point, we actually look at the degrees of freedom in the denominator and the degrees of freedom in the numerator. And we know that that was 2 and 12. So we got down 2 and 12, and we find 3.88 is our critical value. Notice the bold value is what the critical value for 0.01 would be. In this case, though, we're just looking for 0.05, 3.88, and it is less than the value we calculated. So there is a statistically significant difference somewhere. So that's the omnibus test. The omnibus test told us that there is a difference that exists between groups, but it doesn't say which groups are different. Which groups are different from each other is a post hoc test. So again, the omnibus test just says, overall, there's a significant difference, and the chances of it occurring due to just pure chance is less than 5%. Now we actually have been released to do post hoc tests, additional analysis. These basically act as pairs of a series of paired t-tests, but we are no longer worried about inflating the alpha of the significance because we already know that we are correct, there's something different. We just need to find the difference. So we compare each group to determine which mean differs, and it tests all comparisons. Now, it's not actually a series of t-tests. It's one single value we're going to use to look at the means to find out which ones are different. So the most common technique we use for this is called the Tukey's HSD, or honestly significant difference. Determines the smallest difference between means that is honestly significant. It computes HSD. It computes the different scores between means in all conditions. It's going to give us one value that we're going to compare to any of the differences. So again, the significance has already been calculated for us. We're no longer caring about p. We're not calculating p. The equation is ms within divided by small n, so the n of one particular group. So we need to know the degrees of freedom within and the k, but we also need to know q, and q is the standardized range statistic. We get q from that actual chart that we got earlier. So in this particular case, once again, we had 3 different groups, for example, so K number of treatments, we had 3. The degrees of error is 12. It tells us 3.77. That is our Q. So we're going to go to a chart to get the Q. Once we have Q, we're just simply going to put that equation in. So we have the Q, 3.77. We know our mean of squares with N. So the bottom of the equation was 5.33. And our N per group was 5. So 5.33 divided by 5 is 1.07. We take the square root of that, which becomes 1.03. And we multiply that by our Q statistic, 3.77. It equals 3.88. Any mean difference greater than HSD is a significant difference. So let's take a look at that. So we have a mean of 8, 4, and 5. So the difference between criminal and unknown is 3. That's smaller. That's not significant. The difference between non-criminal and unknown is 1. That's smaller. That's not significant. However, the difference between criminal and non-criminal is 4. That is greater than 3.88. Therefore, that's our significant difference. We could have multiple significant differences. There could be multiple, group 1 and 2 and 3 could all be different from each other. But in this case, there is one difference that's actually meaningful, and that's the one we talk about. So again, just talking about this, again, the difference between criminal and non-criminal is 4, criminal and unknown is 3, non and unknown is 1, and again, we just compare those, only one of them is significant. So the nature of the effect, criminals had higher antisocial tendencies than non-criminals, and there was no other significant differences. And again, we're looking at the fact that we've calculated our F, we have all this information, we can now report it. If we were using SPSS, we would be getting the same information, but it would be actually provided in a chart here. So this is actually an example of a much larger F. So again, we have study type here. We have the between groups info, the effect. We have the error info. And if we take a look at this, we then have our F statistic. So again, if we actually took our study type, our effect, the top of the equation, divided by the bottom of the equation, we'd get 14.932, which is F. It would be significant at 0.000. Again, we'd report that as less than 0.001. And the partial eta squared would be given us as well, which is the effect size. It's roughly analogous to an actual correlation. So this is basically explaining that about 50% of the variance is being explained. Actually, 0.52, it would be squared. So again, that tells us kind of the variance. And we'd want to think about what that actually means. And partial eta squared is what we're going to be looking for as the effect size for ANOVAs. Again, there are multiple ways that you can look at effect sizes for ANOVA, but the most commonly reported is the partial eta squared. And again, partial eta squared, generally 0.01 or smaller is considered small, even if significant. 0.09 or smaller is considered moderate, and if it's over 0.25, it is considered a large effect. So this indeed would be a fairly large effect size. So hopefully that gives you some ideas of both how to hand calculate the F, what we're doing with the F, the difference between the F, which is the omnibus test, and then finding where those differences are, and also how we calculate this by hand, but also where we get the exact same information from SPSS.